Claims about the world around us are made all the time, and maybe we don't always have the answers to whether or not those claims are accurate. But hypothesis testing is a statistical method that we can use to determine if those claims have any merit or not. For example, someone made a claim that most internet users utilize two-factor authentication. This is a process that helps secure online accounts. This claim could be written mathematically as P, a population proportion, is greater than 1/2. That is what we mean by most, more than 1/2. In order to do a hypothesis test, we need to take the original claim and then form a contradictory claim. So if the original claim is that the population proportion is more than 1/2, the contradictory claim would be that the population proportion is less than or equal to 1/2. We have two hypotheses here. The one that includes equality is called the null hypothesis. The other one is the alternative. In this case, the alternative hypothesis is the original claim. We'll get into what that means in the next video. I just want to go through the overview of hypothesis testing, so let's move on. We can take a sample of the population and determine the proportion in that sample that uses two-factor authentication. So let's suppose we survey 926 internet users and we find out 15.2% of them utilize two-factor authentication. We are going to compare that proportion to the null hypothesis. And in this case, this is in agreement with our null hypothesis. And it's pretty obvious that it's in agreement. But what if we took a sample and we found in our sample 99.9% use two-factor authentication? This seems like it's in agreement with our original claim, but notice we're going to compare this to our null hypothesis. This is contradicting the null hypothesis. What if we took another sample and we got a proportion somewhere between those numbers, around 50.1%? Again, this feels like it might agree with the original claim, but we're going to compare this to our null hypothesis. 50.1% is larger than 1/2, which would contradict the null hypothesis. However, natural variation would explain such a tiny difference here potentially, if we knew what the spread of our sample data looked like. So we're not convinced that sample 3 is contradicting the null hypothesis or in agreement. Maybe we take another sample, and again we get a percentage that looks like it's contradicting the null hypothesis. However, it's so close to being in agreement with it that we're not sure if this is extreme enough for us to say, this sample represents a situation that tells us the null hypothesis cannot be true. Hypothesis testing is the formal method that allows us to determine if sample results are extreme enough for us to reject the null hypothesis. Here's the basics of hypothesis testing. First, we have to determine a significance level. Often we use 0.05. That tells us the area in our rejection zone. So in this case, for our population parameter, a proportion, we would use a normal distribution and we divide the area under that curve into two regions, the rejection zone and the fail to reject region. Those two regions are separated by our critical value. And these are similar to the critical values and the significance levels that we talked about when we built confidence intervals. A larger confidence level caused a smaller alpha, and a smaller alpha caused a larger critical value. We're looking at a right tail test where the rejection zone is in the right tail of the normal distribution. And notice that when we have a larger rejection zone, that would result from a larger significance level. So small significance level, small rejection zone, large significance level, large rejection zone. The test statistic comes from our known sample data. So we gather a sample, collect the data from the sample, calculate a test statistic like a proportion, and then we find the z-score for that test statistic. We place that z-score on our map of the rejection zone and fail to reject region, and we determine what to do with the null hypothesis from there. If the z-score falls in the fail to reject region, then we fail to reject the null hypothesis. If the z-score falls into the rejection zone, then we reject the null hypothesis. Let's go back to the claim about internet users utilizing two-factor authentication. We have a null hypothesis that our population proportion is less than or equal to 1/2, and that is the claim that we're going to decide to reject or not reject using the hypothesis test. We'll take our sample data, the two that we were unsure about, the 50.1% proportion, and we'll calculate the z-score. That comes out to a z-score of 0.06, so that's very close to the center of our distribution. That is in fact in the fail to reject zone. So if we had gathered data from a sample and found that 50.1% of that sample uses two-factor authentication, we would fail to reject the null hypothesis, meaning we don't know if it's true or false. And that means we don't have enough evidence to support our original claim. If we could reject the null hypothesis and say there's no way that this is true, we would be able to say there's sufficient evidence to support our original claim. But that's not the case for that sample data. What about the sample that resulted in 52.6% of users utilizing two-factor authentication? The z-score for that proportion is 1.58, which again would fall in the fail to reject region. So for both of these sample data that we were unsure about whether or not they contradicted or agreed with the null hypothesis, we found that there was not sufficient evidence to reject the null hypothesis, meaning those two sample proportions were not contradicting the null hypothesis. Our conclusion for this hypothesis test is that there's not sufficient evidence to support the claim that more than half of all internet users utilize two-factor authentication. With a sample that has a proportion much larger than 50.1% or 52.6%, you could imagine that the corresponding z-score would be larger than our critical value at 1.645, which would place us into the rejection zone. Now, if that's the scenario that we're dealing with, then we would reject the null hypothesis because our test statistic landed in the rejection zone. When you reject the null hypothesis, you can say that there is sufficient evidence to support the original claim. However, that wasn't the case for this hypothesis test.